All right, today we are diving deep into the world of our digital guardians. We're talking about the network-based intrusion detection and prevention systems. These are the unseen security guards that have the monumental task of spotting a single tiny threat hidden inside trillions, literally trillions of digital messages. So, how on earth do they do it? Let's find out. So here's our game plan. We're going to start with the dangers lurking in all that network traffic, and then break down the anatomy of data itself. Then we'll meet our digital guard, see the two main ways it can watch the network, figure out how it thinks, and finally, see how it actually stops the bad guys.
And really, this is the central challenge, isn't it? In a world just flooded with an unimaginable volume of traffic, how does any system possibly find that one malicious signal in all that noise? This is the exact problem a network-based IDPS is built to solve.
Okay, let's start by setting the scene. We need to understand the environment our Guardian is working on. The modern network is, well, it's an incredibly high-speed, complex place. But that very speed and complexity can also be the perfect hiding spot for those with bad intentions.
You can think of it just like a real highway. Most of the traffic is totally normal, people going about their day, but some vehicles might have sinister purposes, and it's exactly the same online. Those data streams can be hiding malware or even attackers who are just scouting your network, looking for a way to break in. And that's exactly why this kind of security is so incredibly critical.
So to understand how we catch these threats, we first need to get a grip on how data actually travels. It's not just one big blob of information flying through the wires. It's a highly organized process. Kind of like a digital postal service, really. Data travels in four main layers, almost like a package being prepped for shipping. First, at the application layer, the data is created. Think of an email you're writing. Then, at the transport layer, it gets packaged up. After that, the network layer slaps an address label on it. And finally, the hardware layer physically sends it out. With each step, it gets wrapped in a little more information. We call this encapsulation. And our digital guard, well, it has to be able to see through all of those layers to do its job.
So with that, let's officially meet that guard. This is the hero of our story, the network-based intrusion detection and prevention system, or just IDPS for short. The real heart of the IDPS is its sensor, and you can think of this sensor like a guard with superhuman hearing. See, normally your computer only pays attention to data that's specifically addressed to it, but an IDPS sensor uses what's called promiscuous mode to listen to every single packet that flows by. It's basically eavesdropping on the entire network conversation, all to keep you safe.
So our guard is listening. But where it's positioned on the network completely changes its power and its purpose. There are two fundamentally different ways to deploy one of these IDPS sensors. Okay, this is so important to understand. On the left, you've got the inline sensor. This is like a security checkpoint at a border crossing. All traffic must pass directly through it to get anywhere. So its main goal is prevention. But on the right, you have the passive sensor. This is more like a security camera watching the highway from an overpass. It sees a copy of all the traffic, but the real traffic just flows by totally uninterrupted. So its main goal is detection. This distinction is absolutely crucial.
And this right here is the power of being inline. Because all the traffic has to pass through the sensor, if it sees a malicious packet, it can just drop it right on the spot. Gone. It acts as a true gatekeeper, blocking an attack before it can ever reach its victim.
The passive sensor, on the other hand, is just an observer. It sees that malicious packet go by and immediately sounds the alarm. It sends an alert to the security team. Now, that intelligence is vital, but because it's only looking at a copy of the traffic, it can't reach out and stop the original packet. It reports the crime, it doesn't stop it while it's in progress.
So whether it's inline or passive, how does the IDPS even decide what's bad in the first place? What's going on inside that sensor's brain? Let's get into the intelligence behind the whole operation.
Well, modern systems usually use a combination of three core methods. First up, you've got signature-based detection. This is basically a most wanted list. The sensor has a huge database of digital fingerprints for all the known attacks, and it's constantly checking traffic to see if anything matches. Second, there's anomaly-based detection. This method is smart. It first learns what normal traffic looks like on your specific network, and then it flags anything at all that deviates from that baseline. And third, stateful protocol analysis. This one is all about understanding the rules of the road. It checks to see if a digital conversation is following the expected grammar and sequence for that protocol. All right, the sensor has detected a threat, the alarm bells are ringing, now what?
What actions can it actually take? This is where that difference between an inline and a passive deployment becomes crystal clear.
This table lays it all out pretty nicely. Just like we saw, the inline sensor's biggest superpower is that it can act like a firewall. It can just block the traffic. Done. It can even alter malicious content on the fly. A passive sensor? Nope, can't do either of those. Now, a passive sensor can try to end a bad session by sending reset commands to both ends, a technique called session sniping. But honestly, that's often too slow to be really effective. Both types, though, can usually reconfigure other devices, like telling a nearby firewall, hey, block this attacker's address, now.
Okay, now for a quick reality check. These systems are incredibly powerful, but they are not magic. Historically, they were kind of notorious for false alarms, false positives. Modern systems are way, way better because they combine all those detection methods we talked about, but they're still not just plug and play. They require a lot of careful tuning to learn what's normal for the specific network they're trying to protect. And here it is, the single biggest challenge, the Achilles heel for any network-based IDPS encrypted traffic. If the traffic is encrypted, the sensor can't see what's inside the packets. It's like trying to inspect a locked steel box. For attackers, encryption is basically an invisibility cloak, letting them smuggle their attacks right past the guards completely unseen. And there are a few other limitations to keep in mind. Under super high traffic loads, sensors might just get overwhelmed and have to drop packets, potentially missing an attack. Attackers also know this, and they'll try to blind or crash the IDPS itself. And of course, it's a constant cat and mouse game, with attackers always inventing clever new ways to evade detection.
So, what's the key takeaway from all this? Well, it's that a network IDPS is an absolutely vital layer of defense. But the technology alone is not enough. Its effectiveness really boils down to two huge decisions: its placement, that choice between active prevention or passive detection, and its configuration, tuning it perfectly to your specific environment. And that leaves us with one final thought. We've seen how these systems work today, but the threat is always changing, always evolving. As attacks become faster, more automated, and even stealthier, relying on things like AI and hiding in encryption, what does the next generation of our digital guardians need to look like to even keep up?